45 degree, then you will get the dark rings, dark spot at the center. Okay, so let's do some maths, how you can get this kind of. So what is the objective of this experiment is, two objective you can think of. The first thing is to find out the refractive index of any unknown liquid. If you just design a system where you have planar convex lens and in between some liquid is placed, okay, then you can find the refractive index of this liquid. Another aim is to, you can find the radius of curvature of this convex lens. Okay, so let's do some calculation. So this point we are considering as the radius of curvature of this convex lens, and this small r is at a particular point from this O. Just look at this point. So we are just looking at particular point from O. Is this R, and you can see here the distance between this planar convex lens and the glass plate is varying. So 0 at where it is touching this planar convex lens and the glass plate, and it is increasing if you go either side of this point. Okay, so now it will be very simple. Suppose this you are taking as a D at a particular point, then this will be a square root of r square minus small r square, and this is the incident light normally, okay, to this glass. Okay, so now you can approximate, you can write this D as r, this small d as capital R minus this square root of r square minus r small r square. Then you can just do the Taylor expansion and approximate to first order, then you will get d as half small r square upon capital R. So now we are giving some index here, dn. Okay, so this will be half rn square by r, and here we are not giving any index to r, this capital R. This capital R is a constant for the convex lens. Okay, now we will see this kind of pattern through the traveling microscope. Yes.
Sir, where do they interfere?
Okay, so where they interfere. So go back to this one. Okay, so this incident light is normally falling on this planar convex lens. Okay, and then what is happening here, now you just focus on this one. Okay, so this is refracting in the lens, and then it is again reflecting through this curved surface, and then it is refracting to another medium. It may be air or it may be unknown liquid. Okay, and then you have a glass plate, so it is reflecting, and this 1 and 2 ray are interfering. Okay, so interference between this reflected from the glass plate and reflected from the convex lens.
Sir, the reflected ray will again pass through the lens now.
Yeah. So this is just to show you oblique incident. Basically, the use of this G1 is to give you the all incident ray vertically to this glass. Okay. So this kind of yeah.
Sir, can you please tell what is D here in this figure?
Oh, okay. So D is the gap between this plano-convex lens and the glass plate, and which is a variable. So D equal to 0 where these two are touching to this glass plate. Okay.
That means D is the thickness of lens.
No. D is not the thickness. D is the gap between this lens and the plate. So you see,
Yes.
D is 0 here. It is increasing. Okay. So at particular R we have taken this as D, and then if you change the R, okay, means different rings, radius of this different ring. That's why this n is variable. So dn will also change. Okay.
Yes, sir.
So now you will see this kind of rings, which is called Newton ring, and you can view this by traveling microscope. Okay. Now just calculate the path difference. So the path difference, which will be 2d, mu is the refractive index of the air. Here you can take, if nothing is there, then you can just take air, and mu will be 1. But we are just keeping this mu for any unknown liquid or any other thing.
So the
Okay?
D here is same as Dn.
Yes, but we see here we are not giving any index. So if you just write the index, then you have to give the index for this one also. Okay, because D is variable. Okay, so you have 2D mu cos theta r plus minus lambda by 2. This plus minus lambda by 2 is coming because of the what we have here is the phase change. Okay, 180 phase change. So lambda by 2 is there, and it may be plus minus. Okay. Now rays are incident normally, then you can just write this theta r as 0. Okay. So for the bright fringes, you have this path difference will be n times lambda, and if you just substitute n times lambda here and take it this as 1, then 2d mu and then plus minus lambda by 2 equal to n lambda, and you can write this 2d mu as n plus half lambda. So this is for the bright fringes, and for the central dark fringe where d is 0. Okay, so the path difference is just lambda by 2. Okay, and for the dark fringes, if you just substitute this lambda delta here, path difference, then this is just n plus half lambda, and put back to this number here 2d mu plus minus lambda by 2 equal to n plus half lambda, and this will give you 2d mu equal to n lambda. Okay, so this is for the dark, this is for the bright, and you have for dark central fringe, you can just put this condition.
Can you again explain
Sir,
the
what is
interference between which two beam take place means which way?
what is theta r, sir?
Theta is the refraction angle in
Sir,
the
for
Can you
incidence,
explain why plus minus lambda by 2 is adding in the delta
okay.
equation, sir?
Yeah, so okay, just look at this one. So what you have, if it is in the same medium, then did you recall when there is a change in phase when reflection takes place? Okay. Suppose
Yes,
you
sir.
have just think about you have a glass plate here. Okay, I can just suppose reflecting surface, and is incident, and it is reflecting like this. So what will be the phase change here?
180 degree.
180 degree. Okay, now suppose you have a thick film here, and so you can just draw a normal, and then you have a refracted beam. Okay, and then you have another reflection here inside this medium, and then you have transmission. and then you can just draw from the normal, maybe more. Sorry, it will be like this. And just with this one. Okay, so there is always during the reflection you have a phase change of pi, and that is equivalent to lambda by 2. Okay, so you can write this expression, this plus minus lambda by 2. Okay, got it?
Sir, how theta r
Yes,
is
sir.
0?
How?
Theta r is 0.
Theta r, okay, so for normal incidents, so what will happen if you have like this situation, okay, the theta r will be very
Sir,
very small. Okay,
Sir, the incidence we are considering is on the curved surface, right?
yes, yes, so the angle what we are writing here is very very small. You can just write to 0, and then this will be just 2 d mu. Okay, this is very very small.
Approximately.
Yeah, this should be just approximate sign. Okay. Okay, so now for the bright ring, you have the condition 2d mu equal to n plus half lambda, and for the dark ring, you have 2d mu equal to n lambda, and where n you can take 0, 1, 2, and so on. Now we have calculated this d, the gap which is variable, in terms of small r and capital R. So we can just replace this small d with half a small r square upon capital R.
Slide.
Yes.
Sir, could you show the previous slide once again? Sir, here you have taken bright fringe for n lambda,
Yeah, yeah,
and the next
yeah.
slide you are.
Yeah. No, so the condition is coming like this, na? See.
Yes, okay.
Okay.
Yes, sir, got it.
So we just replace this d with approximation of first order term, half a small r square upon capital R, and then you will get the radius of the bright rings, the square root of n plus half capital R lambda by mu. So this lambda by mu you can write as lambda mu sometime. Okay, that is the wavelength in the gap medium. Okay, so this is not in the lens. Okay, this is here the gap between this lens and the plate, that is the mu we are talking about. Okay, so this lambda mu you can write. So what was the aim? To find out the radius of curvature of the lower surface of the plano convex lens, which is capital R. So you can find out by this equation, mu r n plus m whole square minus rn square upon m lambda. So see here what we have done, we don't know exactly for the bright for the dark ring central fringe, okay, how many n's are there involved. So we can take any unknown ring, and then we have to take the differences.
Sir, what did you say?
So suppose you just take 10th ring. Okay.
No, sir, for bright fringe, what we don't know.
No, for the dark ring, central dark ring. Okay, this is spot central dark fringe. Okay. Just like okay, just look at this graph. Okay. This one. So it is very tricky to measure the difference between this for the bright fringes. So if you take any two different point, so how you can measure? Through the microscope, you just put the cross wire on this tangent of this ring. Okay, take two different position, and then you measure the traveling distance of this microscope, and then you can measure the radius of the ring accurately for variable position of the ring. Okay. So just like I can show you here, the experiment you are going to perform. Okay. So this is just the procedure, and then you have, okay, see the data table. Okay, what you have to do, you can measure the movement of the microscope either through the left or right. So you can just move. Okay, so this one either to the right or to the left. Okay, and you have rings over here centered at O. So main scale, vernier scale, then you have total, and then diameter of n plus mth, you are writing r1 minus r2, then measuring their square, taking the m1 minus m2, and then these things, and finally you can measure the radius of curvature of the lower surface of the lens. Okay, and you can estimate the error. So this is the experiment you are going to perform. Okay, and if a liquid of refracting index mu is introduced between the lens and the glass plate, the radii of the dark ring would be this one you can use here. So m lambda upon lambda into r upon mu. So if you know the radius of any mth ring, then you can calculate the refractive index of the particular medium placed in between the lens and the plate. Okay, so this is
Sir,
one
sorry, sir,
application.
I did not
Yes,
understand the formulas of R.
this one.
Yes, sir.
Okay, so how you can calculate this? So basically, you can do this calculation from either this equation or this equation. Okay.
Where in our dark equation,
Yeah,
there should be by mu.
you just vary the index. Okay. Hello.
Hello, sir.
So you vary the index, and then you can find this expression.
Okay, sir. Okay.
Okay. You just check the Rn and n plus 1 and then subtract it. That will give you. It's very easy. Okay. Just do
Sir,
a,
but here for different value of n plus m or and n, r will be different. But
yeah.
the one we are using, the r must be constant, right?
The
Because
small
we are
r.
using, no sir, capital R
Capital R will be always constant. Yes.
for any value of n and m.
Yes. Capital R is constant for the lens. That is a static. You are not changing the lens. Okay. So
No
this will
sir.
be a static, and this is the aim of the experiment to find out capital R.
Okay.
Okay. So basically, what I was telling you in the experiment, you move the microscope cross wire from one ring to other ring and see the difference. For each ring, you have to calculate this radius. Okay, from the left side and right side, and take the average and these things. So that is the experimental part, but the final expression is just from this step you can get it, putting just the index. Okay, so how you can realize with the pair of image method. So this is you can just think of having a mirror, okay, and you have a source here. Okay, so source is where? Just think about this. Where is the source? You have main source is here, but you have extended source here. So this is the secondary source you are getting. Okay. So the source is somewhere, you have this R, capital R, and then source is somewhere here. So you can see the red dot, and you can see the blue dot. Okay, so reflection from the concave surface of the lens produces S double prime, which is in red, okay, and reflection
Sir,
from
please
the
repeat it.
glass plate.
Sir,
Oh, yeah, okay, so this is slightly changed. No, this is fine. Yeah. Yeah. Yes. Some question are there?
sir एक बार फिर बता दीजिए
Which one?
ये सोर्स डार्क वाला कैसे है?
Oh, okay. So the radius of curvature of this red lens. Okay. Somewhere here you have. Okay. It's very high compared to this one. So that's why we are taking in the calculation this U and R. So you place the source here, which is the extended source you are getting from the glass plate, which is placed at 45 degree. Okay. Now it is reflecting from this red surface here, the curved surface you have, and you have the blue surface which is flat. So now you can see reflecting from the curved surface is giving you some extended image here, S double prime, and reflecting from the blue surface is giving you S prime. Okay. So you can realize this is fine. So
Yes, sir.
now you just consider the distance you measure from this optical axis. You have U where you put this source, means the glass plate we are talking about. Okay, this one. So this is the distance of the source. Now the image from this one is giving you at this point. This is U, and the image from the red, the curved surface, that is giving you S double prime. So this we are writing this V. Distance between these two, we are taking this as small d. Okay. Now you can just realize this d as this one, this distance. Okay. So basically d is variable here. Now you can use very simple mirror equation. So what you have, 1 by u plus 1 by v equal to 1 by f. Here you have v is negative, so you can write 1 by u minus 1 by v equal to 1 by f, and that you can write in terms of radius of curvature 2 by r. Then you can just simplify this. Can you just work out? So v equal to u r divided by r minus 2u, and what we have taken here is the source is the distance u where we place the source is very small compared to the radius of curvature of the lens. Okay, and d is of course very small. So and this d you can write v minus u, and you can put the value of v from as here. You just solve this d, and that will give you for the first order approximation to u square upon r. And what we had when we do the first calculation on the second page, so we had d as half small r square upon capital R, and this we are equating to n lambda by 2. Okay, and then you can write Rn square. This is we are talking about what? Dark rings. Okay, so Rn square as n lambda r. You can put the value of r here. Okay, n lambda, and then you can place 2u square upon d. So basically you can calculate the nth ring radius using this equation.
Sir,
Yeah.
sir, I have a doubt. How did we take the sign conventions in the mirror equation? Means I am confused in that.
Okay, so how you do that? It means in the positive x-axis you have all distance are positive, in negative axis you have all distance are negative. Okay, You measure from this 0. Okay.
Sir, so here our object is S dash for the mirror.
Which one?
Which is the object for the mirror, sir? S dash or S? I am confused
No,
between.
these two are images. This blue and red are the images of this S.
Sir, how can one object produce two images for the same combination? Means
Okay. So now in this combination, what you can think, you have a partial reflecting surface. This red one. Okay, that's why it is going
yes.
towards this blue one. Okay, then there is a difference. Suppose if you just draw a ray passing through this O optical axis, so what will happen? These two will merge.
Yes, sir.
Okay, so this D is variable. This is just a realization of the same setup. Same setup, we are just realizing through mirror. Okay. So here D is
Okay,
variable. Okay.
So we are neglecting refraction in all places. Means that is negligible like that, because that will also produce some turn in the angle of ray.
Yes. So that's why what we are taking here, theta r is very small. We can approximate to 0. Okay, when it is normal.
Okay, sir, understood.
So application of this Newton ring. So one application I told you this one, to measure the refractive index of the liquid, unknown liquid between this lens and glass plate. Also, you can find the radius of curvature of the lens. Another one in industry they use to find out the Young modulus of a metal or Poisson ratio. Okay, so this is not in the syllabus. If you want to go through this, then you can just read, and if you have any doubt, then I can discuss this. But very briefly, what you have, this B and B prime is a rod, and you want to find out the Young modulus for this given rod. So what we have to do, the setup is like this. You have another rod connected with this one and connected to some load. So this you can vary for different M. And there is a setup here. You have another two rods where this mount is there, and this is your Newton ring produced and viewed through the microscope. So when you put some load, then what will happen? This will bend. This rod will bend. This will go up. This will go also up. So you have to measure the difference. Difference between these two glass plate and the lens, and that you can see the changes in the formation of the rings. Okay, so maybe the rings will appear or disappear depending on the separation. Okay, so these are the formula. If you are having some interest, then you can just go through that. Okay, but the simple setup is like this. Another experiment is called Cornu method. Okay, so this is very simple to the Newton ring experiment. Here you have a bar.
Sir?
And yes, yeah.
Cornu method is in our syllabus.
No. These two are not in the syllabus. This is just
Okay,
application we are reading. Okay, these 2 and 3 are not in the syllabus. But if you have interest, then you can just go through that. Okay. So you just put this two load and you know the distance between this hinge and this load, then you can just use this formula to find out the Poisson ratio or Young modulus of the rod. Okay. Okay, so now we have done two different experiments. One is the Michelson experiment, interferometer. Another is the Newton ring experiment. So Michelson experiment, we have done maybe 2-3 class back, where you learn that you have one static mirror and one is the variable position mirror, and then the image orientation, if it is parallel or some incline or cross, so that will give you different kind of fringes. Okay, it may have circular fringe, it may have the parallel lines or some curved lines. So depending on the image of the second mirror compared to the fixed mirror. Okay, so that will give you different rings. Now in the Newton ring experiment also you have seen that you are getting some circular rings, and you calculated the radius and radius of curvature and so on. So these two experiment can be realized by just a simple mirror setup. So what you have here, you have M2 as a plane mirror,
Sir,
and yes.
we are trying to perform these two experiments simultaneously.
No, this is just a realization. Okay, so you can combine these two experiment and we can realize this through the simple setup of two mirrors. Okay, and suppose you just change this distance between this plane mirror and the curved mirror. This A is variable. If it is touching these two mirror, then you have Newton ring experiment. If you have a gap, then you have Michelson ring experiment. Okay, so now what you have, so you have a source which is extended source. You are putting a plate G, okay, that is giving you very you can have equal intensity source. Okay, that is the function of the glass plate we are putting at some angle in Newton ring experiment. And also you can have in the Michelson experiment, where you can see, if you recall the setup, then after the source you have some lens where you get equal intensity out of that. Okay, so now this M1 mirror is partially reflecting, so it can go to the M2 the ray. So now you can see on the extended source you have many point sources. Okay, so you can consider 3-point source just for simplicity, S and S prime and S double prime. Okay, now you can have the image of these 3 extended sources by this mirror M1 and mirror M2. Okay, so this will give you the image of this from the red one, the curved one, and then you have the blue one from this. Okay, so this is giving you the image of this extended source here. Okay, now this is the distance between these two extended source. So these two are coherent, these two are coherent, these two are coherent source. Okay, produced by the same source. Okay, so this is the source S prime, and it is giving you these two images. This one is giving you these two images. For this one you have these two images. So if you look at these two images, they are coherent. These two images are coherent. These two images are coherent. But if you take any cross, this one and this one, this one and this one, or any cross thing, they are incoherent. Okay, so now for the coherent source, this will produce this rings, okay, in their line of action. Means if you just combine this, then this will form the ring about this line. Okay, so these two source, coherent source, will produce this kind of circular rings. Okay, these two will also produce some circular rings. These two will produce also circular rings. But if you just extend this, then somewhere you will get a plane where you will have just one ring. Okay, one ring means a set of fringes centered at some optical axis, this optical axis. Okay, so this position is fixed. You just vary, then only at one position, suppose P, you will get this kind of pattern. But other position, if the images are diminished, you will not get a fine image. Okay, so this is the localization of the image. Okay, so now do some calculation here, very similar to what we have done in the 2 slide back. So this kind of thing. So here D is 0, or distance between these two mirror is 0. So you have here A. Now 1 by U minus 1 by V, same formula you can use, and then this D you can write this as 2A plus U minus V. Simple calculation is there. So this 2D is, you can write 2A minus 2U square, just put back this value of V here, and R minus 2U. You can also use the triangle, similar triangle method, and you can find the magnification. So you can use this 2 triangle here. So L minus V, this is the L distance you have for the localized plane where you have these fringes. Okay. Okay, so this L is very important. You have to find L where you can have localized fringe. So localized source produces non-localized fringe, while non-localized source produces localized fringes. Okay, this is very important.
Sir, what do you mean by localized?
Okay,
Yes, sir.
localized means, okay, so now you have just one plane or one point on this optical axis where you can see this nice fringes. Otherwise, if you just move this plane P to Q, then you will have this kind of overlap. If you go to another place, then you will have something different. You will not have fine fringes. You cannot estimate any property of those fringes. Okay, so this is the localization of the fringe.
Then localized source, how does it produce non-localized fringes?
Okay, so here what you have, the non-localized source.
No idea, sir.
Okay, so now you see you have this extended source. Just consider this. Okay, so at different position you have this. We are just taking 3 S prime and S double prime in this setup. Okay. Okay. So this is producing the images like on the plane G1 and G2. So this is what you have, non-localized. Okay. This one is, these two are non-localized. This is just a virtual image, and that is producing a localized fringe. If you just consider only 2 of these, then you will getting these fringes. 2 of these giving you these fringes. 2 of this is giving you these fringes. Okay.
Sir, so S dash and S double dash exist at the same time or one at a time?
This one.
Yes, sir. All the
This-
3 sources exist.
Exactly at the same time. You see, if you just consider this is the same setup we are just dealing with. Okay, so you have a source, and this is falling on this glass plate G1, which is at certain angle 45 degree or so. You have to maintain it, and then it is, we are just considering 3 point sources on this G1. Okay.
Will there be any difference in fringe pattern in Newton and Michelson?
Definitely. So what you have read in the Michelson interferometer, okay, so we will just see these kind of changes. Okay. So what we learn here, you have this D is the distance between these virtual sources, the coherent source we are producing from this one. Okay, so we are writing this as 2a minus 2u square upon r minus 2u, and the localization distance L is A by A times R by U. Okay, so now,
Sir, but the pattern is same, right, in Michelson's as well as Newton's ring?
yeah, but that depends. Suppose you have some inclined or wedges like condition or crossover, so you have even a straight fringes or you have curved fringes, but Newton ring is always giving you rings. Okay.
But in this case, we have three sources, and there will be no case of the curved fringe or the straight line fringe.
Yeah. In this case, this is just the realization of that. So we are not talking about how they are, their mirror is placed. Okay. We are just, okay. So we will see the condition. Okay. So you have two equations. L is the localization of the fringe, which we are writing this as A times R upon U, and the D is the distance between these two coherent sources. So this is 2A minus 2U square upon R minus 2U. Now, in case of Michelson ring, okay, so yes, yeah. In Michelson ring, what you have, this is also a plane mirror. Okay, this is not curved mirror in the Michelson ring. Okay, so for plane mirror you have R is infinity. So R is infinity, then L will be infinity, and if you just substitute R as infinity, then you have just D as 2A. So Michelson rings are localized at infinity, and it requires a telescope to view them. You have to use a telescope to see those Michelson rings. Okay. Now, in case of Newton ring, come back to here. So the distance.
Telescope.
Yeah.
Telescope or microscope.
Yeah.
Oh. Okay, sir.
You got it?
Yes, sir.
The
Yes, sir.
image is at infinity.
Okay.
Okay.
Yes, sir.
So in case of Newton ring, this distance is 0. This is placed.
So do we have a telescope at a campus?
Oh, let us see. We have, but not at that extent. For observatory.
I guess that is only for PhD students and researchers and professors.
No, not like that. But you may have some tool, but not of that great resolution, maybe.
Can we use, sir?
I don't know exactly. I cannot answer yes or no, but definitely you can ask the in charge. Then you can visit. Okay, if they give you permission also. Okay. Anyway, so in case of Newton ring, the distance between these two mirrors is 0. Then L is 0. Okay. So and A is 0, then you have some negative of this one, this whole term. So we are just taking the magnitude here, D. So Newton rings are localized at the site of mirror, okay, and require just microscope to view them. And the negative sign here I have just mentioned. Negative sign shows the position of G1 and G2 are reversed so that localization plane coincide with the site of M1. Okay, so this is all about the Newton ring, and we have cut down some syllabus from the optics, and okay, so what are the things we are not covering? Thin film, multiple beam interference in thin films, okay, and Fabry-Perot interferometer.
So thin film is same as color of the films.
Yeah, so maybe
Sir,
if you just see the lecture notes. Hello.
Yes, sir.
If you see the lecture notes,
Sir,
page
tomorrow.
number 68 and page number 69, 68, 70, 71, 72. So starting from 68, Stokes relation. Stokes relation basically we have seen in the electromagnetic theory also. So very similar to that. So Stokes relation, 68, page number 277. we are not covering. Okay.
Okay, sir.
From Shastri book.
Yeah. Lecture notes from the Shastri, GP Shastri, GP Shastri and RS Saraswat. Okay.
Okay, sir.
Okay. So now, just introducing this diffraction. Okay. Maybe we will continue tomorrow. Diffraction and grating and polarization. 3 topics we will
Excuse me,
cover.
sir.
Yes.
Sir, means that the just above the Stokes relation, that finite thickness part till that is coming from interferometer.
Yes. So yes, you are right. Fringes of constant thickness, constant inclination. I have done, but it is not a part of your exam. Okay.
Sir.
Yeah. Yes.
Sir,
Which
will be not a part of.
So 68 to 77, I told you. Okay. So I will email you, huh? Yeah.
Some mathematical interpretation of Lloyd's mirror, Billet's split lens, and Fresnel double prism. All these things will be in this test, na?
Yeah. That is, we have covered this in the when you divide the fringes from the wavefront. The amplitude and wavefront we have discussed. So that will be there.
Okay, sir.
So do we have